this lesson, we're looking at De Moivres theorem. Essentially, it's looking at complex numbers raised to a power. So we're looking at z to the power of n. So in component form, this is a plus bi to the power of n, and obviously we could address that using Pascal's. That becomes quite difficult when we get to large powers. If we have a focus in polar or trigonometric form, then what we're looking at is modulus cis of the argument raised to the power of n. And so this comes out as modulus raised to the power of n and cis n times the angle. So this rule here is our De Moivres. Okay. Now, if you're unsure of where that comes from, we do know that if we took z to the power of 3, then we'd be looking at modulus cis of the argument multiplied by modulus cis of the argument multiplied by modulus cis of the argument. And that would be the modulus multiplied by itself 3 times. And with multiplication in polar form, we add the arguments, so it would be the argument plus the argument plus the argument, and you can see quite clearly there that that would be modulus to the power of 3 cis 3 times the angle. That just shows us how De Moivres works, but for us, we'll just be applying what we've got highlighted as the rule above. So really, we're going to look at a couple of examples here, and that will be the lesson. If you look at the following example, it's already in trigonometric form. Doing this in component form would be very difficult, raising to the power of 9. And same with power of 7 and that division. So what we'll look at here is how simple this is. We have cis pi on 3 raised to the power of 9, which will simply be, because there's nothing in front, it means it's a 1. So we have 1 to the power of 9, cis 9 times pi on 3. And so here we just get cis 9 pi on 3 is 3 pi. Now this 3 pi is not within the given domain. It's not between negative pi and pi. So 3 pi, that's 1, 2, 3 pi. So it's the same. It's coterminal with pi and negative pi. So we can say this is cis pi. So a nice simple simplification there. When we look at part B, and we've got cis 7 pi on 4 over cis pi on 3 all to the power of 7, we apply De Moivres to the denominator. So we have cis 7 pi on 4 in the numerator, and on the denominator it becomes 1 to the power of 7 cis 7 times pi on 3. And that simplifies down to cis 7 pi on 4 over cis 7 pi on 3. Now, because this is a division and we're in trigonometric form or polar form, then we can divide the modulus and subtract the arguments. So we get 1 over 1, which is just 1, cis. And we have 7 pi on 4 subtract 7 pi on 3. And so that will just be cis. Lowest common denominator is 12. So that makes this 21 pi on 12 and 28 pi on 12, which gives us cis negative 7 pi on 12. Now that's within the expected domain, so that's our final answer. So all we're asked to do is simplify. We don't have to put it into component form, we can leave it in this trigonometric form. Alright, so we'll look at another example. Okay, so when we look at this example, this is more the intention of De Moivres. So we have in component form 2 complex numbers raised to powers and divided. What we're going to have to do is first put them into polar form, then we'll go through the process of applying De Moivres and simplifying. So to to simplify this, it's much easier using De Moivres than expanding out and then trying to apply Pascals both to numerator and denominator. So for the top, we're going to call that a. So a to the power of 3 is 1 plus I to the power of 3. Now if we take this over here and we look at a, the modulus of a will be 1 squared plus 1 squared, so that'd be square root of 2. And the argument, it's in quadrant 1, so it's nice and easy. It's just arctan of 1 on 1, which is equal to pi on 4. So that means that a cubed is simply root 2 cis pi on 4 cubed. Now if we look at b to the power of 5, then, which is 1 take root 3i to the power of 5, then the modulus of b will be square root of 1 squared plus root 3 squared. And so that's going to be square root of 4, which is 2. And the argument is arctan of root 3 on 2. Now just be careful here because it is in quadrant 4. We're going across and then down, so this angle will be negative arctan of root 3 on 1, and so we end up then with pi on 3. So now we have that, we can say that b to the power of 5 is simply 2 cis negative pi on 3 to the power of 5. And so now we can simplify. We can look at 1 plus I to the power of 3, 1 take root 3i to the power of 5 is equal to root 2 cis pi on 4 all to the power of 3 over 2 cis negative pi on 3 all to the power of 5. So root 2 to the power of 3 is 3 times pi on 4 over 2 to the power of 5 is 5 times negative pi on 3. So when we split this up, we end up with 2 root 2 over 2 to the power of 5, which is 32. And we have cis 3 pi on 4 subtract a negative, which makes it plus 5 pi on 3. So we get root 2 on 16 cis. Common denominator is 12 again, so multiply by 3 here and we get 9 pi on 12. And multiply by 4, so we get 20 pi on 12. We have root 2 on 16 cis 29 pi on 12. So we're going to need the coterminal angle here. So it's 1 full rotation plus an extra 5 pi on 12. Because 1 full rotation is 24 pi. So if we subtract that 24 pi on 12, we end up with root 2 on 16 cis, and we're left with 5 pi on 12. Now if we wanted to, we could expand that back out into our component form, but we're going to leave it in our trigonometric form because this is not going to be a nice outcome. All right. Hopefully that makes sense. It's simplified doing it this approach. We could still use Pascals to expand out each and simplify the other way, but this is going to be a much nicer answer. Okay, in this last example, it's going to be quite a complex application. So we've got a proof question here, and it's asking us to prove that sine 4 theta is equal to 4 cos cubed theta sine theta subtract 4 cos theta sine cubed theta. So we're going to take the approach here that we can get this using De Moivres, and that we can get this using Pascals. So these are two expansions of the same thing, but we need to start by taken a little bit of a jump, and we can say that cis for theta is the same as cos for theta plus sine for theta I. So we're going to look at the left-hand equation consisting of this, which is the same as looking at cis theta to the power of 4. So now we're looking at the right-hand equation, and same deal, we're going cis theta all to the power of 4, and this is where we use Pascals. This is cos theta plus I sine theta all to the power of 4. And using Pascals, that means we're going to use the coefficients 1, 4, 6, 4, 1. And following this through, we start with 1 cos theta to the power of 4. And then we've got 4 cos cubed theta sine theta, 6 cos squared, don't forget the I, sine squared theta I squared. We have 4 cos theta and then sine cubed theta I cubed. And then finally we have 1 sine to the power of 4 theta I to the power of 4. This simplifies nicely. We have cos to the power of 4 theta. We have 4 cos cubed theta sine theta I, so that doesn't change. I squared is -1, so we have subtract 6 cos squared theta sine squared theta. I cubed is the same as saying -I, so we have now -4 cos theta sine cubed theta I. And then finally I to the power of 4 is just 1, so we're left with sine to the power of 4 theta. Now, because we're trying to prove sine 4 theta, then it means it's the imaginary components that we're looking for. So the two imaginary components we can see in this side, sine 4 theta is imaginary, and in this side we have this 4 cos cubed sine theta and -4 cos theta sine cubed, and they're the only imaginary components. So if we equate the imaginary components of both sides, we get sine 4 theta is equal to 4 cos cubed theta sine theta. Subtract 4 cos theta sine cubed theta. Now, I believe that is what we're trying to prove. These types of proofs are relatively simple in the sense that we're just looking at two approaches using De Moivres and Pascals to relate. We can look at a lot of different trig identities using this approach, multiple sum identities, where this isn't really the focus of the course, but this is a good application of De Moivres, so you can see where it can be used in some more complex scenarios. Okay, so that concludes the lesson. Make sure you understand the first two examples fully, and hopefully you can get your head around that third example.